So this is a video to help us understand confidence intervals. So we had a study in an earlier activity in which we had a sample of 124 kissing couples, and 80 of them leaned their heads to the right. So we're going to try and figure out, well, a confidence interval relating to kissing couples in the population and which way they lean their heads, whether they lean to the right or to the left. So first it says identify the observational units and variable in this study. Well, the observational units are the kissing couples because that's, well, that's who we observed, right? And the variable is which way they turned their heads. Did they turn their heads to the left or did they turn their heads to the right? So I wrote that down here in red so you can kind of refer back to it. Then it says describe the sample data numerically and graphically. So this is a categorical variable, turning heads to the left or right. We would probably say that it is a binary variable. It can only be to the left or the right. I guess you could kiss straight on if you wanted to, but we're looking at it being binary. And if I was to graph it, since it's categorical, I know it's going to be some kind of a bar chart. You know, maybe it could be a pie chart. That's not all that important right now. But describing the sample data numerically, well, that is kind of important. Really what they're asking me for is a statistic. And I want to know, well, what is the proportion, because that's what we deal with when we're dealing with categorical variables, the proportion of kissing couples who lean their heads to the right. So that proportion, since it is from a statistic, since it is from a sample, that is a p hat. And in this case, p hat is equal to 80 divided by 124 are 80 couples, divided by 80 couples that turn their heads to the right, divided by a total of 124 couples, and that equals 0.645. So we're going to see that 0.645 come up a lot in not only this problem, but in future problems as well. That is our p hat, our sample proportion. So now we're going to get to the meat of the problem, and we're going to try and determine a 95% confidence interval for the population proportion of all kissing couples. So we're looking at the entire population of kissing couples and figure out, well, what is the confidence interval for those who lean to the right? Well, what I want to do here is I really want to determine whether or not I can use the central limit theorem on this problem here. Because I would like to know, well, if I went out and got, hundreds of thousands of samples of 124 kissing couples. So I went out and I got 124 kissing couples and I found the proportion for that group that turned their heads to the right. And then I went out and I got another 124 couples and I got the proportion for how many of them turned their heads to the right. And I want to know whether or not if I put all of those samples together, the proportions together, would that give me a normal distribution? That's really what the central limit theorem is all about, is whether or not I can take essentially an unlimited number of samples and find out their proportions and whether or not that distribution of those proportions would actually be normally shaped. And the way I need to test that is I say, well, does my n, that is the number of samples, times my p hat, is that greater than 10? And likewise, is n times 1 minus p hat greater than 10? If those two conditions are met, and if the sampling was random, those two important conditions here, then I can use the central limit theorem. So let's find out. Well, my n was 124, and my p hat was 0.645. So let's pull up a calculator here, and let's find out. Is 124 times 0.645, is that going to be greater than 10? Well, sure enough, it is. That is equal to, well, just approximately 80. So it's approximately 80, which is definitely greater than 10. What about 124 times 1 minus 0.645? Well, let's go over here and we go 124 times 1 minus 0.645, and that's 44. So let's make sure I get that color there. So that's approximately equal to 44, which is also the greater than 10. So what it's telling me is that I can use the central limit theorem in this problem to do this analysis. So let's erase this picture right here that I did a minute ago and get one that's a little bit bigger and easier to use. So this represents every single sample that I could take of 124 kissing couples. So n is equal to 124, and the proportion of them that lean their heads to the right. And I am looking at my particular sample of 0.645 as being right there in the middle. That right there is my p hat. That is the proportion that I got from my one sample of 124 kissing couples. And what I'm trying to find out is, I mean, that might or might not be the population proportion. But what I want to find out is if this represents here 90% of all kissing couples, what is the lowest possible proportion that that I could have as my population proportion, and what is the highest possible proportion that could represent my population proportion? So to do that, I need to know a couple of things. I need to know a z-score that represents this upper limit here, and I need to know a z-score that represents that lower limit over there. And these will actually be the same z-score, except that this one over here is going to be positive and that one's going to be negative. And they're going to be the same z-score because this distance right here is equal on both sides of my statistic. And I'm going to end up using a formula to calculate the confidence interval of p hat, my statistic, plus or minus this special z-score, which I designate with an asterisk. It's called the critical value. I'll write that here. Critical value times the standard error, which is kind of like our standard deviation. So what I'm trying to find out is the actual proportion right here and the actual proportion right here that represent the lower and upper limits of this 90% confidence interval. So I know what my p hat is. My p hat is this right here, this 0.645. I'm going to calculate what this z-score is, and I'm going to calculate what my standard error is. So let's start with the z-score. Now, I did hand out a sheet that had this information on it. So I can see that at a 90% confidence interval, the z asterisk, the critical value, is going to be 1.645. But I want you to know how to calculate that in case you don't happen to have this in your wallet or your purse or your notebook. So the way I would calculate this z asterisk right here is I would say I know that from way over here is 0% of all the data, and way over here is 100% of all the data. So I know that from here to right in the middle is 50%, and I know that from the middle to over here where I want to get is half of 90%, because 90% is the confidence interval I'm looking for, and it stretches all this way. So half of 90% is 45%. So I know that this z asterisk, this critical value, is sitting right at the 95th percentile, 50% plus 45%. So I can go to my calculator and I can do inverse norm, plug in 0.95, which is my percentile, because inverse norm, you put in the percentile, and I'm going to get a z-score for that spot right there. So let's do that. I'm going to call up the calculator, and I'm going to go second distribution, and I want inverse norm, which is 3, and I'm going to go 0.95, which is my percentile right there, and I'm going to hit enter, and I find out 1.644. Well, look at what this says. This says 1.645. So that is how you would get it. If I was looking for a different confidence level, let's say I was looking for a, I don't know, I'm going to have the most common ones right here. But well, let's just say I was looking for a 70% confidence interval. I'm looking for a 70% confidence interval. Well, I'm going to make the same diagram that I have. I know I have a normally shaped thing. I know that my middle right here is my p hat, and I'm looking for, instead of 90%, a little bit narrower here, I'm looking for 70% confidence interval. So I want to be less confident than 90%, but it's going to be a number that's going to be closer to my p hat, as you can see, because it's a narrower distance right there. So I'm going to do the same kind of a logical thing. I know that over here is 0% of my data, and over here is 100% of my data. So from 0 right to the middle, well, that's always going to be 50%, because the middle is 50%. From the middle over here to where I'm looking for my z asterisk, well, that's going to be half of 70, which is going to be 35. So this is at the 85th percentile. Well, I would go second distribution, inverse norm, 0.85, and I would find that the z, did I do it right? Yes, I did do it right. That the z-score at that point is equal to 1.04. It makes sense that the z-score is less than, say, at the 80% confidence level that I have up here in the chart, because 80% is going to be wider than 70%. And that's going to get me a critical value that would be even bigger than 1.04. So it's important for you to understand how to calculate your critical value. And for those of you watching this who don't have the TI-84 calculator, you probably know how to do what I just did there on using your tables. So back to the problem. I found that my z-score here, my critical value, was equal to, oh, no, I forgot what it is, so I'm going to look here, 1.645. So I have 1.645, and I have to multiply that times my standard error. That is, I have 1.645 standard errors, or I oftentimes think of it as standard deviations away from the mean. But if I don't know what that standard deviation is equal to, then it doesn't help me get the exact proportion that I'm looking for. I'm trying to go from, really what I'm trying to do eventually here is to be able to use the z equals y minus y bar over s to find this actual number right here, or actually I'll be able to do it using this formula that I've given you here. But I need to calculate what is the standard error, right? If I don't know that, then I can't finish the problem. And the standard error is equal to, see, I'm getting kind of crowded here, so I'm going to stop and erase something. The central limit theorem tells me that I can calculate the standard error. I can calculate the standard error using the formula, the square root of p hat times 1 minus p hat divided by n. So that's a formula you need to remember, and it's really kind of astounding. So the standard error in this particular case is going to be the square root of 0.645 times 1 minus 0.645 divided by my n, which was 124. So my standard error in this case, I'll just calculate it over here, 0.645 times 1 minus 0.645. And I'm going to divide that by 124. Let's divide that by 124. And then let's take the square root of that. And I find out I have a, let's call it a 0.043. 0.043 standard error. Now I have all the pieces I need to calculate my confidence interval. So I have p hat. So here's the formula I'm using right here. I have p hat, which is 0.645, and I'll do the plus before I do the minus, plus my z asterisk, which is 1.645. That's just coincidental that it's 0.645, times my standard error of 0.043, and that gives me 0.645 plus 1.645 times 0.043. That means this upper boundary over here where I was adding, this is p hat plus that, would be 0.716. And if I go back and I do it with a minus. So let's highlight that right there, and let's change that from a plus to a minus. No, I did it wrong. Oh, I erased the whole thing. Okay, sorry. 0.645 minus 1.645 times 0.043. And I get the lower end of my confidence interval right here at 0.574. So my confidence interval, I would write like this. I would say my confidence interval is 0.574 to 0.716. And what that's telling me is that I am 90% confident that the actual population parameter, the actual percentage of people who turn their heads to the right, is somewhere between 0.574 and 0.716. If I went out into the population and got thousands and thousands of samples of 124 kissing couples, and I looked at the proportions of all of those kissing couples and how many of them turned to the right. What I'm saying is that 90% of the time, the proportion would be between 0.574 and 0.716, or if I turn them into percentages, 57.4% would be turning to the right, somewhere between 57.4 and 71.6% would be turning to the right. So if I kind of go back to, well, I guess I'm not going back to it, but part E is asking me right here, well, based on these intervals, does it seem plausible to believe that half of all kissing couples leading to the right? Well, you know, I'm back here looking at my pictures, and I'm thinking, well, 90% of the time, 90% of the time, it's going to be between 0.574 and 0.716. I mean, 50%, 0.50 is way out of the confidence interval here. So no, I don't think it's plausible to believe that 50% of all kissing couples lean to the right. I don't think that's the case. Is it plausible that maybe 2/3 of all kissing couples, or 0.667, turn to the right? Well, let's look at our picture again. Well, 0.667, that's kind of, let me, come on, draw this here. 0.667, well, that's in my 90% confidence interval. I mean, you know, it's possible that that could be the actual population parameter. And then the next question, it says, well, what about 3/4? What about 0.75? Maybe 3/4 of all people turn their head to the right. And I come back to my study, and I'm thinking, well, I don't think so. I mean, 3/4 is 0.75. That's kind of far out there, you know. So this whole process that we just did is a really important methodology for taking a statistic and then being able to infer some information about a population. Because if you remember, we just started out with a sample of 124 kissing couples. And from this, using the central limit theorem and using this process of finding a confidence interval, we can really make some inferences about the entire population. We can say we are 90% confident that between 57.4% and 71.6% of the population turn their head to the right, well over half. I'll just point out finally that the last part of this problem said, comment on whether or not the technical conditions necessary for these confidence intervals to be valid are satisfied. And that's really where we were checking the central limit theorem, whether n times p hat is greater than 10 and n times 1 minus p hat is greater than 10. Those are two important numerical conditions, and the other condition is that the RAN DOM is that the sample has to be random. These two things have to be satisfied, and we were good, and we did it in the very beginning of the problem.